How does motor inertia impact precise motor control? Imagine trying to stop a moving car suddenly or accelerate quickly without losing control. That's similar to what motor inertia does in a motor system. It's all about how much resistance the rotor has to changes in its spinning speed. This resistance depends on how heavy the rotor is and how that weight is spread out around the axis of rotation. The more mass and the farther it is from the center, the higher the inertia. When you want to change the speed of a motor, you have to work against this inertia. Think of it like trying to spin a heavy wheel versus a light one. The heavy wheel takes more effort to start or stop. In motor control systems, rotor inertia plays a big role in how smoothly and accurately the motor responds. If the rotor has high inertia, it resists sudden changes, which makes the motor run more steadily. This is good when you need constant speed, like in fans or pumps. But it also means it takes more energy and time to speed up or slow down. So, high inertia motors are slower to respond but tend to be more stable. On the flip side, low inertia rotors can speed up and slow down quickly. This responsiveness is perfect for robots or machines that need rapid movements. But with low inertia, the motor can become unstable or oscillate if the control system isn't tuned right. Engineers often have to find a balance between stability and responsiveness. A motor with high inertia resists sudden changes, giving steady operation but slower reaction times. A motor with low inertia reacts fast but might overshoot the target or shake. To manage this, control systems use sensors like encoders or resolvers to constantly check the motor's position and speed. These sensors send feedback to the controller, which adjusts the electrical signals to keep the motor on track. Proper tuning of acceleration and deceleration rates helps prevent oscillations and energy waste. When a load is connected to the motor through a shaft or coupling, the relationship between the rotor's inertia and the load's inertia becomes very important. If the load's inertia is much higher than the rotor's, it can cause resonance issues, making the system unstable. Engineers need to consider the stiffness of the coupling and the inertia ratio to avoid these problems. If the load is too heavy or the coupling is too flexible, the system might vibrate or oscillate. That's why matching the motor's inertia to the load and tuning the control system carefully is essential. Choosing the right motor size depends on the application. For precise positioning in robotics or satellite systems, the motor's inertia must match the control system's capabilities. If the inertia is too high, the motor will need more torque and time to reach the desired position. For applications like fans or pumps where constant speed is needed, higher inertia can be beneficial. But for quick torque changes, like in industrial machinery or robotic arms, lower inertia motors are better. Electrical and mechanical inertia also interact. The electrical properties of the motor, like resistance and inductance, influence how it responds electrically. Modern control systems use software algorithms to compensate for both electrical and mechanical inertia in real time. This allows for more precise control, even with varying loads or conditions. In summary, rotor inertia affects how fast a motor can change its speed, how stable that operation is, and how much energy it consumes. Engineers must carefully match the motor's inertia to the specific needs of the application and tune the control system accordingly. Proper understanding and management of inertia ensure the motor performs reliably, accurately, and efficiently in all kinds of electronic and embedded systems.